Hey, how's it going, everybody? Alright, you're back with Mr. Klinkerman. We're in section 9.5 where we're going to continue to develop on the ideas that we've been most recently building regarding definite integrals and their applications. And one of the applications that we've already seen for definite integrals is that they can be used to find the area between the x-axis and a curve. And what we're going to do today is we're going to be finding the area between two curves. So not between a curve and the x-axis, but just the area between two different curves. Alright, so that's our learning goal. We're going to be finding areas between two continuous curves on a closed interval. And we're going to do that under a couple different circumstances. And let me go ahead and start showing you the first one of those. Alright, I've got a diagram here. And I told you we're finding the area between two curves. And pay attention to the way that I've got this set up. What we're going to do is we're going to find the area between this curve that I labeled as y1 and then the curve, I know it's straight, but it's still called a curve mathematically, between that curve that I labeled as y2. Okay, and we're going to do that on the closed interval from when x is equal to a to when x is equal to b. Alright, now I want to show you something that I hope you would think of if I had asked you to do this kind of thing geometrically. Alright, if you were trying to find the area between those two curves geometrically, I think you would agree with this. The area between curve y1 and y2 would be equal to the area of the higher curve minus the area of the lower curve. Alright, so the area of this curve right here, y1, minus the area of this curve right here, y2. Let me write that down. And then I'd like to illustrate to you on the diagram how this works out. Alright, I'm going to highlight what I mean by the area under y1 right now. I'll show you in the picture where that is. Alright, here's the region for the area underneath y1. Alright, and similarly, this would represent the area underneath y2. Alright, and if I just want to find the area between the two, I just have to take away this bottom area, the area where they overlap. I have to subtract that from the area that's kind of only under the top curve. Alright, so area under y1 minus the area under y2. And so, how do we find that? Well, you know how to use definite integrals to do this. We can say that the area under curve y1 is equal to the integral from a to b of function y1 with respect to x, and then the area under curve y2 would be the integral from a to b of whatever function y2 is with respect to x. Alright, now if we use a property of definite integrals in reverse right here, what we can do is whenever you have a sum or a difference of two integrals with the same limits of integration, they're both being integrated from a to b, we can just combine this into a single integral. Normally you'd do this the opposite way, but we're going to combine these two integrals into a single integral. And that would be an integral with the same limits of integration from a to b. And it would just be of the difference between those functions y1 and y2. Alright, if you ever want to find the area between two curves, it's simply using this little formula right there. You find the difference in the two functions, y1 minus y2, and then you integrate that over the interval from a to b. So whatever interval you want to find the area for, you set that is your lower and upper limits of integration. Alright, now let me show this to you, the rule, with a few of the guidelines that go along with it. Okay, this is straight from your book. If you have two functions y1 and y2 that are continuous on an interval from a to b, has to be continuous. So you can't have any asymptotes or holes in the graph on that interval. And here's the other thing I may or may not have pointed out, y1 is greater than or equal to y2 for all x's in the interval, then the area between y1 and y2 from when x equals a to b is given by the same expression that I just showed you. All right, now let me go back and talk about this part right here where y1 has to be greater than or equal to y2 for all x's in an interval. Okay, you can see here that between points A and B, this curve y1 is always higher than that curve y2. And that's what's going to differentiate this video from the next one. Is that in the next one, we're going to make it so that maybe y1 is above sometimes and maybe it's below at other times. All right, but you'll see that in the next video. Let's go ahead and practice a problem where we're going to find the area between two curves. Okay, you see what we're trying to accomplish. We're going to find the area of the region bound by these two functions here, x squared plus 1 and 2x plus 1. All right, now there's several considerations that you have to take into account whenever you're trying to find the area between two curves. One of those is you need to know which function is on top, and the other is that you have to know what is the interval that you're integrating for. And in order to do that, it's very helpful to be able to see the graph of each of the functions on the same set of axes. All right, now often this will be a GDC problem for you, but I want you to see how to do it without a GDC as well. And you know how to graph simple functions like a parabola and like a line, so you'll understand where I'm getting this picture that I'm about to draw right now. Now truly all I need is the general shape of these two things. You know that f of x would be a parabola whose y-intercept is going to be 1, and it would be centered along the y-axis. And so there you go, there's that parabola, there's our f of x. And then g of x, you know that the line 2x plus 1 would have a y-intercept at 1. And then it would have a slope of 2, so you'd go up 2 over 1, up 2 over 1, and so forth. It would look like this, roughly. Okay, so what we're going to end up trying to find the area of then is going to be this little region right here between the two curves. I'm going to go ahead and shade that in. And so hopefully this will make sense to you. What we're going to be doing is we're going to be finding the area. And the way we're going to find the area is we're going to find a definite integral. We'll talk about what the limits of integration are here in a moment. But we're going to find the definite integral of g of x minus f of x, the higher curve minus the lower curve. With respect to x. All right, so now, how do we find those limits of integration? Well, not as difficult as you might think. We need to know what the x-coordinates are at these 2 points where the curves intersect. And whenever you want to know where two curves intersect, all you have to do is set the equations of those two curves equal to one another. So what we're going to do is we're going to solve the equation x squared plus 1 is equal to 2x plus 1. Watch this. Alright, so I made a note here that we're trying to find intersections, and we're doing that simply by setting the two equations equal to one another and then solving. When you set the two equal to one another, you've got a quadratic equation, so we'll set that equal to 0. Let's subtract 2x from both sides and subtract 1 from both sides. We'll get x squared minus 2x equals 0, and then we'll get x times x minus 2 equals 0 if we try to solve by factoring. And so the 2 points of intersection are going to happen when x is equal to 0 and when x is equal to 2. Now what we'd really like is to know what the x and y coordinates for those points of intersection are. And so what you can do is simply plug in 0 and 2 into either one of the functions, and I'll show you how that gives you the same answer in both instances. If we plug in 0 into this function x squared plus 1, we're going to get 0 plus 1 is 1. But if we plug it in right here, we'd still get 0 plus 1 is 1. So on both of those graphs, whenever x equals 0, y is equal to 1. So we know this point of intersection over here, the first one, is the point 0, 1. All right, and then we're going to plug in 2. Well, 2 squared plus 1 is going to give you 5. Or if you do 2 times 2 plus 1, you're going to get 5. Again, it didn't matter which function you plugged it into because this is the point where the two functions had the same y value. So we know that this is the point 2, 5. So what we need to do is think about horizontally, what is the lower limit and what is the upper limit of integration? Well, 0 right there is going to be the lower limit of integration. 2 is going to be the upper limit of integration. So when I go back and try to make my area function, I'm going to integrate from 0 to 2. As such. All right, now let me clear some room on here so that you can see the rest of what we're going to do. All right, the rest is just simply using what we know about calculus, right? We're going to go ahead and make this the integral from 0 to 2 of, all right, now we're going to g of x minus f of x, so that's going to be 2x plus 1 minus x squared plus 1. All right, with respect to x. And I prefer to go ahead and actually do the subtraction with those functions. If we do that, we're going to have a negative x squared plus 2x dx. All right, and then simply we're going to go ahead and find the integral. You know that the integral of negative x squared is going to be negative 1/3 x cubed. And that the integral of 2x is going to be x squared. And we're going to evaluate that from 0 to 2. Okay, so we'll plug in 2 into this expression, and we'll plug in 0 into this expression, and then we'll find the difference between them. Of course, the 0 is not going to make any difference because both terms will be 0 when I plug in 0. So really, I just need to plug in 2 here. And if I plug in 2, I'll get negative 1/3 times 8 plus 2 squared. So that's going to give me negative 8/3 plus 4. And negative 8/3 plus 4 is the same as negative 8/3 plus 12/3, and that's 4/3. Okay, so the area between those two curves is equal to 4/3. And it was pretty simple. All you got to do to find the area between two curves is find the definite integral of the higher function minus the lower function over the interval from A to B. All right, you've already done this in class actually, so hopefully this is just a review for you. Make sure you watch the next video where we're going to make it so that the curves aren't always, it's not always the same one on top or the same one on bottom. All right, I'll see you in the next video.